Hi there, this is part 3 of the video collection for related rates. So we're going to continue with this problem. In part 2, I had asked you to set up this problem for part A with the picture with variables and identify your d what's, and then try to come up with the formula that relates to variables. So let's look at the situation. So we have a boat is being pulled in by a winch on a 20-foot tall pier. The winch pulls at a rate of 2 feet per second. At the instant when the boat is 15 feet from the base of the pier, the question is, how fast is the boat moving? So then the first thing we want to do is then come up with what is the picture. So we have a boat is being pulled in by a winch on a 20-foot tall pier. So that's what the winch is at the, I assume, at the top of the pier. So you have that height, and then the winch is pulling a boat that is somewhere far out in the water, and so it looks like we're going to have a triangle. And so let's label the things that are changing then. So we have, well, first of all, the pier is 20 feet tall, so let's put that in here. So that's the height, so that's 20 feet, and this is not changing, right? The pier doesn't change in height. Then there's a winch up here, right, that then is pulling the boat. So there's a boat somewhere over here. Pardon my great drawing here. And so the boat is being pulled by the winch. Maybe not quite like that, but you get the idea. So as this is being wound up, right, then this rope or cable that is attached to the boat is going to be pulling the boat closer, so the boat will be moving that way. So this distance will be getting smaller, so let's call that X. So as the boat, right, as the winch pulls the rope or cable, these two distances are changing, so let's call that Y. So when the boat is 15 feet from the base of the pier, how fast is the boat moving? So at some point when X is 15, we want to know how fast is the boat moving. We want to know the rate of change of the boat. So this is what we want to know. So be careful. Again, I mentioned in the previous 2 videos, but be careful not to put 15 in here, because it's not always, this length is not always 15, right? The winch is being wound up, so it's pulling the boat, and as this winds and winds and winds, this distance is changing. So the boat is not always 15 feet away. That this distance is changing. We actually don't know how far the boat is when we start pulling it. So we want to know at the point when it's 15 feet, so this distance is always changing until it's pulled to wherever it needs to be pulled. So there's our picture with variables, and this is a right triangle. So that we did the first step. Draw a picture with variables. Now identify our d what's. So let's see, what are we given? So what rate do we have? And I noticed that I'm giving at 2 feet per second, so that's a rate. That's a rate of change. And as the winch pulls at a rate of 2 feet per second, so that is the distance y. So right, that distance then is changing at a rate of 2 feet per second. So we have dy dt is 2 feet per second. And this is where variables, this is why variables are really important to go with your picture, because then you know how to, what your d what's are, like d what variable. Well, my y comes from, oh, this is the distance that's changing, and I call the y. Somebody else could have called this a and that b or c, because we have a right triangle, right? That could be c, and then this will be dc dt. So the way that you label your shape is going to affect how your d what's look like. So if you don't have variables, it's going to be hard to name what those things are. And what do we want? We want to know how fast is the boat moving. So we want the rate of change of the boat. So the boat distance is being described by x, so that means that we want dx dt when x is 15. right? This x is not always 15, so don't put 15 in the picture. The only thing that's always fixed is the height of the pier. The height of the pier is not changing. All right, so then the third step is to write a formula that relates the variables in the numerators of your dwats. So y and x. And the picture helps because then I know how do I relate x and y in a right triangle. And so we can use Pythagorean theorem, which tells us that normally that a squared plus b squared equals c squared. Sometimes I prefer to remember it as leg squared plus leg squared equals the hypotenuse square. And so in this case, looking at our picture, we have leg square x plus leg square, so it'll be x squared plus 20 squared equals hypotenuse squared equals y squared. And so that's our equation. Do we have just x and y? Yes. So our numerators in the dwats, the variables are x and y. Our equation has only x's and y's. Now remember in the prior video we did the problem with the cone, which I can scroll up real quick. And remember the formula for the cone, the volume was 1/3 pi r squared h, but our dwats only had v and h, so we needed to figure out a way to get rid of the r because we don't have anything about r on our dwats. So here, luckily, we already have just x's and y's. Our dwats have x and y, and our equation has x's and y's. So now we take the derivative with respect to the variable in the denominator of our dwats. So that will be with respect to t. So I'm going to say here, take the derivative with respect to t of both sides, right, implicitly. So this means x and y are both functions of t, so we're going to need the chain rule here. So when I take the derivative of x squared with respect to t will be 2x times dx dt by the chain rule. And plus the derivative of 20 squared is 400, but that's just a constant, not attached to a variable, so the derivative is 0, equals 2y times dy dt. And just to review this again, right, this is by chain rule because, that's my lazy because there, y is a function of t, right, y equals y of t. And so when I take the derivative of y squared, so when I have y squared, that's really y of t squared. So when I take the derivative of that with respect to t, that's going to be 2 times y of t to the first power, and then times by the chain rule the derivative of y of t. So that will be dy dt. Okay, so that's what's going on here. All right, so now we can plug in our values because now we want to solve for dx dt when x is 15. So let's see, when x is 15, let's put everything in. So I'm going to have, what are we going to have? 2 times 15 times dx dt. That's what we're looking for. And this is 15 feet. Equals, right, that's 0, so we don't include that, 2y, oh, I don't have the value of y, times dy dt. Do we know our dy dt? Yeah, that's what was given to us. Dy dt is 2 feet per second. So dy dt is 2 feet per second. So we need to figure out what y is when x is 15. So just gonna draw arrows to what we did here. So we need to figure out y when x is 15. So let's go back to our triangle, and we knew that that was 20. Now I'm going to put 15 here, and I need to figure out what y is. So what is this? So leg square plus leg square, so 15 square plus 20 square equals y square. And so 15 square is 225 plus 400 equals y squared, so 625 equals y squared. So what is that, 25 I think? Yep, so y is equal to 25. So when x is 15, y is 25, so we can go back over here and put that in. Oops, 25. So let's see. So let's now solve it. So I have 2 times 15 feet, so that will be 30 feet, right? So I'm just gonna drop the units for a second. 2 times 25, that's 50. Oh, times another 2, so that will be 50, 100. And this is feet, so this will be feet square per second. And then divide by, we want to solve for dx dt, and this is 30 feet. I said I was going to drop the units, but then I added them there, so let's try to be consistent. So divide by 30, so I'm going to have 100 over 30, and then feet squared divided by feet will just be feet per second. So dx dt is then, reduce that to 10/3 feet per second. Now the one thing here to note is that what is happening in this situation as we're pulling, right, then these is the distances are getting, what would you say, are the distances decreasing or increasing? They're decreasing, right? So one thing I could have done is put a negative here, that dy dt is negative, and then that would have made this here a negative 100. So when I divide by dx by the 30 to solve for dx dt, I will have negative, and that's okay. So then we can say, so you can then put a negative here, but without doing the negatives, you still get, essentially we're doing the rates of change, the absolute value of the rates of change. But when you write it out, I will say then the boat is, the rate of change, or the boat is decreasing, right? So you want to specify that things are decreasing. So how fast is the boat moving? We can say the distance from the boat to the pier is decreasing at a rate of 10/3 feet per second. So let me write that out. So right now we can say the distance from the boat to the pier is decreasing at 10/3 feet per second. Or we can say the boat is moving at a rate of negative 10/3 feet per second. So the negative tells you that then it's decreasing. So depending on how you write it out, right? So again, I could have included saying here, since everything is decreasing, the y dt is negative 2 feet per second, and then put that in my work there, negative 2, and then this would have come to a negative 100, and dx dt would have been negative. And so giving me that answer right away, or just understanding that things are decreasing. All right, let's do part B of this example. Part B is asking, how fast is the angle between the water and the winch increasing? So we're going to use the same picture. So let's see, since the winch is up here, and so that is this, and then the water is over here. So the angle between the water and the winch will then be this angle, theta, right? As you get closer, so that's the angle between the water and the winch. So let's call that theta. So the information is the same. So we still have, so now let me do it negative here. So what we have is dy dt equals negative 2 feet per second. So now I'm going to use the actual negative and see how our answer comes up. And what is it that we want? So how fast is the angle between the water and the winch increasing? So we want to know how fast is the angle. So we want to know how the rate of change of theta. So we want d theta dt when x is 15. So this is kind of interesting because we're when x is 15, but we already know from part A that when x is 15, y is 25. So this is really right, and the reason I'm finding the y is because notice that our dy/dys are y and theta. They don't involve x. So I want to make sure that then my formula involves just y and theta. So when x is 15 is the same thing as saying when y is 25. So let's see. That was not a very good arrow there. Okay. So we have our picture with variables, the things that are changing. And now, let's see. Now notice what's going to be happening as this distance decreases, right? The boat is being pulled, so x decreases, y decreases. What's happening to theta? What do you expect theta to be? Should be increasing, right? This angle, as the boat gets closer, the angle is going to be getting bigger and bigger and bigger. So we should expect theta dt to be positive. So we'll see how that negative comes into play. So let's find, so we have our picture with variables, we have our dy based on our variables. So now we need to come up with a formula that relates the variables in the numerators, so only y and theta. So what relates y and theta in a right triangle? And that will be sine, right? Because we have the opposite and the hypotenuse. So we can say sine of theta is equal to opposite, which is 20 over hypotenuse. And now things are changing with respect to t. So both y and theta are functions of t. So let's take the derivative of both sides with respect to t. So, and let me rewrite this as 20 times y to the negative 1 because I know I have to take the derivative. So the derivative with respect to t of sine theta equals then the derivative with respect to t of 20 y to the minus 1. And let's take the derivative. The derivative of sine is cosine theta. By chain rule, theta is a function of t, so it would be d theta over dt, right? If it was just, if I was taking the derivative with respect to theta, d theta, then this would just be cosine theta, because d theta will just be 1. But here is, we're taking the derivative with respect to a variable other than the variable given. And so here, the derivative of this is going to be, bring the negative 1 down, general power rule, so minus 20 y to the minus 2, then by the chain rule, dy dt, because y is a function of t. So that's where our negative then comes in. So I have cosine of theta times d theta dt equals negative 20 over y squared dy dt. And so now let's remember what was our information, what it was that we have. So we have that dy dt was negative 2 feet per second, and we wanted to know d theta dt when x was 15 and y was 25. So we have y, we need cosine of theta. So let's bring in the triangle again. And what we had was, pretend that's right triangle, 20, and now with our values we know that's 15 and that is 25, and theta is over here. So I want cosine of theta. So cosine of theta is, cosine is adjacent over hypotenuse. So this will be 15 over 25. So that's what cosine of theta is. So let's put everything in, right? I need to know what value to put in there. So that's why I needed my triangle. So then we're going to have cosine of theta. So 15 over 25, let's reduce that actually. 15 over 25 reduces to what? Divided by 5, so that will be 3/5. So let's use the reduced version. So 3/5 times d theta dt, right? So that's my cosine of theta equals negative 20 over y squared. y squared will be 25 squared times dy dt. dy dt is the negative 2. And so notice that's where our negatives cancel out. So what does this become then? Multiply both sides by 5/3 to get rid of it on the left side. So I'm going to have d theta dt equals the negative 20 times negative 2, which is positive 40, over 25 squared, which is 625, times, so we said divide by 3/5, which is the same thing as multiplying both sides by 5/3. So that's my d theta dt, which we can reduce. So this 5 goes into 625, so I can say 40 over 125 times 1/3, and then both of these still have a 5 in it, so 8 over 25 times 1/3, and then just multiply that out. So 8 over 75 is our d theta dt. So what are our units though? Units, theta is changing in radians, and things here are changing in seconds, so that means our d theta dt will be 8 over 75 radians per second. And so that will be the rate of change of the angle. And notice that it is positive. You could change it to a decimal, so you could say d theta dt is changing to a decimal, you will have 0.10666 repeated, so 107 radians per second. Just make sure that everything is done in radians. So that will be our answer. If you're doing the WebAssign homework, make sure that you pay attention to how many decimal places you're being asked to round. If it doesn't say round to a certain decimal place, they're probably expecting the full answer in fraction form. So 8 over 75. All right, and so we'll record one more video or a couple more videos with a couple more problems. So email me if you have any questions.